Thank you all for coming out. This attendance has it's really blown me away, the amount of feedback and participation we've gotten from so many different industries. So again, thank you from the bottom of my heart. Specifically, this afternoon, I want to talk more about the fire side. Dr. Bombic did a great job of explaining thermal runaway and kind of how it takes off. I want to look at it from a post-thermal runaway standpoint. Because that's something that we're currently facing. Yes, great strides are being made in developing new technologies to prevent thermal runaway from happening, but we still have countless numbers of EVs and technology that's out there currently that is very susceptible to thermal runaway. And what do we do with that? So specifically in motorsport, we don't have a ton of examples of thermal runaway and EV fires that have happened. I'm aware of the one instance with a Big Daddy Don Garlett's EV dragster that he made had a problem shortly after leaving the start line. The other two examples that I'm aware of happened in Europe, and they happened during charging. So those didn't even happen on track. They occurred in the paddock, unfortunately caused a lot of damage in the paddock, no injuries, but those were charging-related thermal runaways. I actually need to amend this slide because at dinner with Jimmy last night, I did find out there has been one injury caused by high voltage being somewhere that it shouldn't be, and that was a long time ago, which is why a lot of the red light procedures and red light technology is what it is because of the injury that happened. But we have good procedures in place. I think we have very good procedures in place for handling these red light hot car scenarios, but we have seen EV fires. The fire service has seen plenty of them on the street or in garages, and like I mentioned, we have seen a couple of them at tracks. But the procedures that we have for thermal runaways may be not as clear as the high voltage precautions. So kind of, again, a lot of what's in my presentation is going to mirror somewhat Dr. Bombic's. I'm currently doing some research with a couple of the Batcave affiliate faculty on thermal runaway mitigation. So I've been buried in Google Scholar for the past couple years, and the number of papers that are coming out since like 2019 is almost exponential. The amount of content and research that's being done by universities across the world on understanding thermal runaway and lithium-ion battery fires. And more recently, just looking at Google Trends, there's been a huge spike recently because of the epidemic occurring in New York City. The FDNY is dealing with e-mobility devices causing a lot of structure fires, unfortunately resulting in quite a few injuries and deaths. So it's on a lot of people's radar. So today, just from a 30,000 foot view, I feel there's still a lot of misconceptions out there about lithium-ion battery fire protection and being able to put out a battery fire. So my goal is to really just give factual information on what does work, and Dr. Bombic touched on that a little bit, as well as what doesn't work and what kind of works. So first off, and again, I'm going to expand on what Dr. Bombic shared a little bit. So fire, I've got quite a few friends here from Charlotte Fire Department and my home department, East Lincoln Fire. So fire, it's just heat and light. Combustion is a chemical process which we generally accept as a rapid oxidation process. We view that as combustion. And even taking a step further from what Dr. Bombic talked about, we like the fire tetrahedron now, where in addition to heat, oxygen, and fuel, we also have chemical chain reaction, which again, we generally accept that as an oxidation reaction. Think of like rusting. Rusting is oxidation. Combustion is that just many, 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 many times faster. It gives off a lot of heat. So to put a fire out, you take away any of those four and the fire either doesn't start or you put it out. When we use water, we take away heat, we take away oxygen, the fire doesn't start or it goes out. We use something like an ABC, dry chem extinguisher, purple case, something like that. We're gonna take away the availability of oxygen, and we're gonna interrupt that chemical chain reaction. The fire is gonna go out. Battery fires. So internal short circuit could cause a thermal runaway, which will lead to a fire. Physical damage could cause an internal short circuit, so on and so forth. And none of these really fit within the fire tetrahedron as we understand it. So I'll be a little specific and say that as we understand fire, a thermal runaway isn't a fire. It is a highly exothermic electrochemical reaction. It produces a lot of heat and it will set things on fire. But what's going on inside the cell itself, it's probably going to be hard to classify that as a fire because, again, it doesn't work like the fire tetrahedron works. So for my non-fire professionals, just real quick, when we're looking at fire protection options, we look at our fire extinguishers. They're going to have a class on them. These fire extinguishers are good for certain classes of fire. The red ones that you see hanging on the wall, those are class ABC fire extinguishers. They spray pressurized white powder out of the nozzle. And all those letters mean something. Class A, we call that an ordinary combustible. That's going to be wood, paper, plastics, things like that. The mechanism by which you put those out is, I'm oversimplifying it, but you essentially cool that fuel to the point that it can't sustain combustion anymore. Class B is what, those are flammable and combustible liquids, oils, solvents, alcohol, fuels, things like that. Usually where you have a Class B fire, you have a large availability of the fuel. The common way that those fires are dealt with is generally just remove the oxygen from it. Foam, CO2, really good to displace oxygen, cool it to the point that it won't reignite. Class C, and now we're getting into a little bit of a gray area where there's some confusion with lithium-ion battery hazards and battery fires. Class C is an electrical fire, but even more specific than that, it's energized electrical. So if you have an electrical panel and there's a fire in that panel caused by arcing or a bad connection, something like that, where you get really high resistance and a lot of heat, that's live electricity causing heat, which causes a fire. If you can turn off the power, which you can't really do, you can't turn off a battery. There's energy stored in that cell. You're not really going to be able to turn it off. If you can turn it off, then the fire just becomes whatever else the high resistance or that heat had caught on fire. You can use a regular fire extinguisher for that. But so different than battery energy storage, you can't really look at them the same way. Class D, this is another thing I see a lot of misconceptions about when it comes to lithium-ion battery fires. I've got some slides specifically dealing with these misconceptions later. Class D, and I think both Boz and Jimmy touched on this later. When you see those giant yellow fire extinguishers with copper metal powder in them, stuff like that, the intended environment for those is something like a machine shop where you've got metal chips or shavings or something like that in a pile. I have seen those metal fires. They are hot. They burn clear a lot of times. They're really odd. And essentially, the only way you put those out is just bury it. You bury it under the powder, it takes away the oxygen, and it kind of cakes around the burning metal so that it can't reignite. But we're talking like elemental magnesium, elemental iron, elemental lithium, which isn't something that's present in batteries. Class K, it's a cooking fire. It's just the other class that's not worth mentioning. Okay. So I have several videos in here from the Fire Safety Research Institute, FSRI, their division of Underwriters Laboratory. They've done a lot of work with testing and producing research on what causes lithium-ion battery thermal runaway, how do we deal with it, can we deal with it, the various methods, and kind of comparing and contrasting available technology against the hazard. So I've got a couple videos in here. This was Adam Barrowy from FSRI giving a presentation with De-mystifying at their symposium that occurred this past March or April, I think, or maybe it was last year. I can't remember, it's recently. But his video does a great job of illustrating something that would take me a really, really long time to describe. So we'll watch this here for a minute.
Here's a 4-panel comparison. So no extinguisher in the top left, ABC dry chem on the top right, carbon dioxide bottom right, and water. And so you can basically see for yourself in real time. Again, thermal runaway happens. This is a slightly smaller battery pack, but thermal runaway occurs. We immediately activate whatever the suppression method is, based on the pain there. And you can see everything has some effect. It's not that all of a sudden these extinguishing agents don't work on fire or flaming, but they're not addressing the source of flammable gas release, and they're not really stopping propagation of thermal runaway. The thing that does that best is water, because it's a fantastic cooling agent. It's got a high specific heat. It can absorb a lot of energy. It can vaporize. It's all the great things it's always been for firefighting.
Yeah, but going back to something I said just a minute ago, but wait, I hear you cry. It's called a lithium-ion battery fire, so there must be lithium in it, right? So people that know enough to be dangerous say, okay, I need a Class D fire extinguisher. I need one for flammable metals, the big 50-pound yellow monoliths. And again, that's not, elemental lithium is not what's happening inside a lithium-ion battery. And if you need further proof, here's another video from Adam Barrowy.
And so this is Class D extinguishing agent applied directly to a battery pack. The instant it goes in thermal runaway, there's no response time from someone saying, oh shoot, and then running over the extinguisher. So here is thermal runaway. Here's the Class D agent being poured right over it. And since Class D agents are really meant to sort of smother and encapsulate burning metals, what you see here is the gases from thermal runaway are just pushing that agent out of the way. It can't do its job.
So that should put that to bed, hopefully. All right, the other thing, but wait, I hear you cry. It sure looks like water put out the fire. The FSRI, they had those cells just out in the open surrounded by a little metal cage. Water was able to get inside the cells. So that's easier said than done in practice, because we look at an EV, whether it's a street car or a race car, and these batteries are buried under many, many different layers of packaging. And so where are you putting the water? On the body of a car? Maybe underneath the car? Who knows how many layers of metal, steel, and composite are between the cooling medium and the actual source of the heat.
While water is excellent, it's worth understanding that there's still impediments to water. I think most of us have a pretty good sense of this by now. If you can't get the water to the cells in thermal runaway, then you're basically fighting a losing battle. You're sort of just letting the fuel burn out as thermal runaway occurs. So this is, again, that 50-cell battery pack. We have our automated robot fire extinguisher. And we tried to bank water into that enclosure. So there's a little bit of a hole at the top. And you can see that where we had some limited effectiveness of that pressurized water extinguisher when the pack was out in the open, effectively what we're doing here is not a whole lot. We're just letting the fuel burn out inside that enclosure.
So as Jimmy touched on during his presentation, the battery packs that they've built for IMSA and Formula E, they have included douse ports, which is essentially just a hole in the casing where if you were able to, inject some sort of cooling medium, it would circulate around the cells themselves, not around the casing, but it would actually get in and surround the cells themselves. That's really nice for a bespoke battery and a purpose-built racing series. It would be nice if we could convince OEs that this was also a good idea, because I think it would make the fire service's life a lot easier for these, on the side of the road Tesla incidents. And I don't mean to pick on Tesla, it's just kind of the analog, just like we say Kleenex for, tissue. Tesla's just kind of the analog for electric vehicles, so don't sue me, Tesla. Okay, a couple things, just kind of summarizing these previous slides. So be careful about sales claims from fire protection companies. Again, Jimmy previously mentioned Lithex and some of these other lithium-ion battery-specific fire suppression mediums. I mean, they may have some effectiveness other than just straight-up water, but again, nothing is going to have any impact on a fire that it can't get to. So that's number one. Like the one video from FSRI, everything has some effect on cooling and maybe stopping thermal runaway propagation. But again, if you can't get to the cells, it's all for nothing. Okay, so there are some variables to thermal runaway, and Dr. Bombick talked about some of them, and I'm going to go into a little bit more detail because lithium-ion battery, and I talk to a lot of people, I say, well, what chemistry of lithium-ion battery are you using? And they kind of give me a funny look, and they say, well, it's a lithium-ion battery. Like, well, the exact flavor really does make a difference. And I don't have nearly as many slides from white papers as Dr. Bombick does, but I do like this one. So this is 2 graphs from a paper, which I'd link below. So the left, the cluster of dots on the left is the temperature of thermal runaway onset versus the maximum temperature reached during thermal runaway, and every single one of those dots is a different chemistry. So the ones that are going to give you the most problem are where they're up and to the left. So that means thermal runaway starts at a relatively low temperature, but at its hottest, it gets really, really hot. So the safest one is going to be all the way down bottom left, because it's going to be a low, top, yeah. It's going to be a high kickoff temperature, but a low maximum temperature. Thank you. I had to stare at that for a while to figure out how I was going to describe it, and I still didn't get it right. So the one on the right is the specific energy density versus the rate at which thermal runaway is occurring. So it's the steepness of that curve. How fast is that battery heating up internally? And again, as Dr. Bombick pointed out, lithium iron phosphate, LFPs have shown to be much more stable. You have to get them a lot hotter before they kick off, and then their maximum temperature isn't as hot. And the curve, or the cluster plot on the right, shows that it's also a slightly less steep temperature rise curve. State of charge of a battery also plays a significant role in the severity of a thermal runaway. At 0% state of charge, I will say that's like a theoretical point. If you can get a battery to 0, I mean, you've killed it. You can't even recharge it at that point. I mean, it is like super dead. It's also more or less inert. To get a battery at 0% state of charge to go into thermal runaway, you would pretty much have to set it on fire. So it's very inert, it's very passive. And as you go up from there, again, as Dr. Bombick had mentioned, the more energy you put into a battery, the more energy it has to let out. And it will either let that out electrically or thermally if you abuse it. And again, one last video from Adam Barrowy illustrating that.
So I've thrown in an extra variable here. We're going to take a look at state of charge as well. We've watched the video on the left. Again, we're talking about a cell full of combustible materials, 30% state of charge. There's thermal runaway. There's flammable gases coming out of the cell, and those chemical reactions generate enough heat that this thing turns cherry red. So nice, basic, easy to follow understanding of those chemical reactions leading to what we see. Here's how state of charge can accelerate that. So the energy dissipated when the cell goes through thermal runaway due to the internal short circuit can be very rapid based on state of charge. So on the right, you're looking at 100% state of charge, and that's essentially as severe as it can get. What we tend to see through most of our research is that basically above 75%, it doesn't really matter. As you get down below that, you can start decreasing the rate that the fire spreads.
Yeah, so that was the same battery. The only thing that was different was state of charge. So again, the more energy a battery has to give, whether it's electrical energy or thermal energy, it will give it in one way or another. So I'll just throw this up here because again, the stuff from FSRI, they're smarter than I am at this, so credit to them. That QR code takes you to their symposium website where they have all the videos from all the presenters. It is going to be more audience geared toward the fire service, but Adam Barrowey's presentation, the whole thing was fantastic. Excuse me. All right. So maximizing protection. As far as we know, once thermal runaway has set in, you can't really stop it. What you can do is stop it from propagating. You can stop a one-cell failure from turning into an entire pack failure. But that single cell, by the time you have an indication that that thing has taken off, that cell is gone, and it's more or less too late to intervene for that one cell. To give yourself the best outcome from a thermal runaway situation, it's going to fall into one of three categories. You're going to stop it from happening, you're going to limit the damage, and improper disposal, which doesn't apply so much to this audience, but I'll touch on it briefly. All right, prevent it from happening. I think everybody's presentation I don't think Dr. Bombick's presentation mentioned this, but the key to prevention is knowing what your battery is doing. In motorsport, that's a little bit easier. Again, Williams, Bosch, they get telemetry from all the cars. They know what's happening in all the batteries all the time. They can see things if they start to go south and put a stop to it. We've talked a couple of times about man, it sure would be nice if streetcars had similar technology, and it would be really nice if that information was available through OBD2 or something, but it isn't. So for streetcars running track days or something like that, that becomes a little trickier. If you have any control, if you're designing a battery, if you're developing a battery system, something like that, telemetry is probably one of the more important things that you can engineer into the safety of your system. If you get an early enough warning that something is going south thermally, there are indications that you can provide early cooling to the battery and possibly stop it from becoming a catastrophic failure. So telemetry and data, very important. Okay, match chargers to batteries. Now, I don't know what happened in the Moto E and the Rallycross, the Rallycross fires that happened over in Europe, but they did both happen during charging. And even then, I don't think this is an inaccurate statement, but most of the streetcar EV fires that have been dealt with by the fire service have happened during charging at home, charging in a parking garage, something like that. So there's definitely a link between charging system malfunctions and battery fires. The one thing I will say universally, never, ever, ever, ever just put a lithium-ion battery onto some generic trickle charger. even though motorsport hasn't seen high voltage battery fires, the 12-volt battery fires are more common because teams will put those on trickle chargers, and the trickle chargers aren't smart enough to know when to stop sending current to the batteries, and they will go into thermal runaway. When we were in Long Beach, we talked to the Formula Drift guys, because they had one that weekend. We were there. It was the 12-volt battery that a team put on trickle charger caught fire. So make sure your charging system and your batteries or your BMS, they're paired up and they're meant to be together and they communicate with each other. Store and use according to manufacturer specifications. If you're developing a battery, make sure you know which one of those subchemistries you're using. Make sure you understand what the data sheet for that subchemistry says about its maximum safe temperature, and that, like Jimmy said, they did their own testing to figure out what that kickoff point was and work backward from there. So that may be available as a data sheet from a battery supplier, or if you have the means, which we're getting ready to do at University of North Carolina at Charlotte, we'll set it on fire ourselves and find that temperature the hard way, or the fun way. So limit the damage. That's another way that you can stop a small problem from becoming a big problem. Obviously, if you lose an entire car, that's a big problem. But losing one car versus losing your entire paddock is a worse problem. So, I got to spend some time with Robert Bosworth and Jimmy down at the Petit Le Mans. And at Road Atlanta, there's a spot on the track where they're like, if something really goes south, we're going to drag this car out to here where we can just let it do its thing. If the fire department needs access to it, they have access to it, but we're going to get it away from spectators. We're going to get it away from the other teams, and we're going to just let it do its thing, where if we need to provide other intervention, we can, but it's not in the hub of activity going on at the track. And proper disposal. Again, less relevant to this, just know that batteries that go in the trash, lithium-ion batteries that go in the trash have a tendency to set garbage trucks on fire. So, talk to your recycling companies. There are third parties that will do lithium-ion battery recycling as well. That's even a question I don't have answered at the university. As we generate lithium-ion battery waste, even our hazardous waste vendors, we're not really sure. Now, we have gotten some guidance since then, but it's easier said than done, because there are special procedures that need to be followed, especially if a battery has been damaged or abused or used outside of its recommended use. They do have to be handled a bit differently when disposing. And just something else to think about. Yeah, we can regulate race cars, we can regulate street cars, but anybody can just go to Amazon, throw down $60 and ride around on an e-scooter, take it into a hauler and plug it in to charge. That would be a really silly way to lose several $1 million worth of equipment because you plugged in a $60 e-scooter. So consider that. And be wary of these e-mobility devices, because they really are causing a big problem across the world. All right, next steps. We do need help from the OEMs. We need to be able to somehow know what the status of these batteries are. Again, if we're running a race series like GTP, LMDH, Formula E, where partners like IMSA, Bosch, they have the telemetry. They've built that into their system. They know what's going on. That's great. Somebody that puts a roll cage in their Tesla and wants to go track day it or, turn it into a race car, we don't know, and Tesla doesn't make that very easily available. And again, like Lucid and the other companies, even your Audis, your plug-in hybrids, things like that, it's the same problem. We need to figure out how to get battery status information from these out of the showroom cars. Something else to think about, especially if you have a car that's specifically a race car, we have standards on what a safe fuel cell looks like. It would be silly. Now we know it's silly to go running around in a purpose-built track car with the factory plastic fuel tank in it. You know, a racing sanctioning body wouldn't allow that. Does something like that need to exist for battery casings and battery construction? I don't know. Probably, but who would lead that? And then training for track services. I think events like this are part of it. You know, tracks are understandably a little bit leery about bringing EVs in, because there's a lot of, they know what they don't know, and that kind of makes them just kind of take a hands-off approach because the risk is greater than the profit at this point. And I know there are several tracks here right now, and we're going to have an opportunity for a roundtable after I'm done talking, and I would love to hear from you guys, like, what's holding you back? What questions would you like to have answered before you feel more comfortable about welcoming hybrids and EVs into your facility? I would just be really curious to know for myself. All right, so I actually made really good time, so you're welcome. But my personal acknowledgments, SHEMA is the Campus Safety Health and Environmental Management Association. All these logos, all these groups up here, you know, I wouldn't be able to share this information. This information wouldn't have been able to be brought to you without these folks in some way, shape, or form. So SHEMA kicked off a lot of this. Obviously, the Bat Cave, I'm working with two of their affiliate faculty on my thermal runaway research, Dr. Nicole Braxton and Dr. Shen-En Chen. They've been great, and the work we've been doing is so fascinating. Charlotte Fire Department, they're a great partner with the university. My home department at East Lincoln and Stan 21, who's responsible for the Racing Go Safer Foundation. They've been a tremendous partner as well. So thank you to all those guys.